Hey, Mr. here today to talk about tail behavior. So we have this equation, y equals x cubed plus 2x squared plus x minus 3. And I want to find out the equations or the function's tail behavior, okay? So when we're dealing with polynomials, there's a couple things that I want you to take away. Number one, the degree of the polynomial, okay? The degree of this polynomial is the highest exponent that we see, which it's 3, okay? So the degree for this one, this polynomial is just going to be 3, okay? The leading coefficient is something also that I want you guys to pay attention to. And the leading coefficient is just going to be the number attached to the x which has the highest exponent, okay? And in this case, our leading coefficient is going to be 1. If there is no number, like for example here there is no number in front of x, we can just assume that that number is 1, okay? So our leading coefficient, I like to just abbreviate with LC, is just going to be 1. Now our degree and our leading coefficient actually tells us a lot about this graph, okay? And what I hope for you to know by the end of this video is how to figure out what the tail behavior of a graph is just by knowing the graph's degree as well as the graph's leading coefficient. Like just knowing that, you should be able to figure out what the tail behavior is. Okay, now what's the tail behavior? So let me graph this equation for you real quick. I have it already typed into my calculator. I'm going to go ahead and hit enter and graph that. And you'll notice that this graph looks a little bit like kind of like a disco graph. Somebody kind of throwing their arms all over the place, okay? Now, a tail behavior is, for the most part, what is the graph doing as it moves off the screen, okay? There's two parts to this story, okay? There is this right side of the graph, okay? I like to call it the right arm of this guy. His arm is pointing up. So we'll say that the tail behavior of the right arm of this graph as it goes off the screen is going up, okay? For now, all you have to recognize is that the right arm, and this is what I want you guys to write, is just going upwards, all right? Now, what's the left arm doing in the graph? And you guessed it, it's pointing down, okay? So the leftmost point of this graph is, for the most part, going to keep continuing to go down forever and ever and ever, okay? So the left arm, or the left tail of this graph, is pointing down, okay? Now, what's this whole deal about degree and leading coefficient? Well, here's the deal. If I were to do another degree, okay, similar to 3, for example, another odd degree, you'll notice that I will get for the most part the same result. So let me type in another equation for you, okay? Let me move over here. And this is what I'm going to do. I'm going to do another polynomial, but this time I'm going to raise it to the 5th power, okay? And I'm just going to go ahead and add like maybe 5x squared plus 2x. So when I graph this, okay, you'll notice again the graph looks very similar to the one that I graphed before, and that the tail behavior is the same thing. Come to find out, the more that you do with these graphs, okay, the degree, as long as it's odd, you'll always have the tails always going in different directions, okay? Now, how could I, for example, get the right arm to go down and the left arm to go up, or switch the way the arms move? And you might have guessed it, and that's where the leading coefficient comes in, okay? If I make the leading coefficient negative, you'll see that the arms switch completely, okay? So let me open up a new screen real quick and show you that real quick. So, for example, let's just do negative 2 x to the 3rd, okay? Again, the degree is 3. The leading coefficient is a negative number, negative 2, which means we have an odd degree, or what they like to call an odd function. I'm going to go ahead and graph that, and you'll notice that this has switched the dynamic, okay? So this time the degree was 3, and the leading coefficient was negative. It was a negative 2. And you'll notice that the tail behavior kind of, for the most part, responded a little differently, okay? So let me just write that down. That the left side now is pointing up, and the right side now is pointing down, okay? So that's another variation, okay? So when the degree of a function is odd and the leading coefficient is positive, you kind of get this situation with the tail behavior. And when the degree is odd and the leading coefficient is negative, you sort of, for the most part, get this behavior here, okay, where the left one's pointing up and the right arm's pointing down, okay? So, is there anything else that could happen? And the answer is yes, you guessed it. Here's the deal. Let me go ahead and graph like one of my favorites, x squared, which is everybody knows is to be the parabola. And you'll notice that these arms, they're both pointing up. First of all, let's talk about the equation for a parabola. It's y equals x squared. What's that degree? Well, the degree is going to be 2, okay, the degree of that polynomial. And what's the leading coefficient? Again, it's going to be 1. If there's nothing there, we just list 1. So the leading coefficient is positive. The degree is even this time, and you'll notice that this time the left and the right tail is both pointing up. So there's another option you have. When the degree is even, you'll notice that the tails both point in the same direction. If the leading coefficient is positive, they both point up. Now, there's another option to this, obviously, is where both arms are pointing down, okay? And the easiest way to look at that would be to obviously do the parabola equation again, but this time throw a negative coefficient. This time, let's go ahead and say -3. That'll be our leading coefficient, x squared. And let's go ahead and graph that. Now you'll notice that this graph is pointing down. Both tails are pointing down. So that just shows you that even functions with leading coefficients that are negative will have both of the tails pointing down, the left one and the right one. Okay, so let's just go ahead and write this equation down. The equation I used again was -3x squared. The degree was 2, just like before, except however this time the leading coefficient was negative. Okay, it was -3. And this time our tail behavior was that they were both pointing down. Okay? Okay, to make a long story short, so what we have here is that when we have an even degree and the leading coefficient is positive, our graph for the most part is the left side is going to be pointing up and then the right side is going to be pointing up as far as the tail behavior goes, okay? Now, this isn't going to tell you what the middle of the graph is doing. The middle of the graph could be doing all these waves and stuff like that, but eventually the left tail will be pointing up and the right arm will be pointing up as well, okay? Now, when the leading coefficient is negative and we have an even degree, the opposite happens. Both of these tails are going to be pointing down. Again, we don't know what's going on in the middle of the graph, but at least we know that the tails are both pointing down, okay, for even degrees with the leading coefficient negative. Odd degrees, with the leading coefficient positive, we have one arm up, one arm down when it's an odd degree. Left arm down, right arm up when the leading coefficient is positive, and then the flip when the leading coefficient is negative. And for the most part, that is tail behavior. I would like you guys for now to go ahead and show your answers like this, where you just go ahead and say left arm's doing this, right arm's doing this, and that will give me an idea that you kind of have an understanding for the basics of tail behavior. Down the road, you're going to start writing it a little differently. For those of you guys planning on going to calculus or pre-calc, they start treating these a little differently and they write them a little different, but for the most part the concepts still stay the same. Okay, if you have any questions, call me on over, and hope you have a wonderful day. See you later. Yeah, bye.